Hey guys, today we're going to look at various properties of polynomial functions, so that way we could graph them at the end of this lesson. So first we're going to look at how to classify a polynomial. Now, a polynomial by definition is when you add or subtract multiple terms together. These terms individually are called monomials. That's when you only have one term. Now, when you have one term, you have an exponent. This we label as n, and n would be considered the degree of that particular monomial. In a polynomial, the degree would be the highest exponent that you see. So for example, for a, we have f of x is equal to 3x to the fourth. This would be a fourth degree monomial, and that's because the highest exponent is 4. In this case, since there is only one term, that means we have one term. So that's why it's called a monomial. For b, the degree would be the highest exponent, which is 5. And in this particular polynomial, we have 3 terms. Now, all polynomial functions can be classified by the degree and the number of terms. So here we have various examples, and we're going to do just that. First, we have 5. So let's say if we have some function f of x is equal to 5. The degree here would be 0, and this is because we don't have a variable. So if you do not have a variable at all, that means that there is no exponent, so 0. This would be considered a constant, and that is because if you were to graph f of x is equal to 5, it would be a horizontal line where y is equal to 5. So it's constant. In this case, this is one term, so this is, as we discussed, a monomial. For x plus 4, even though we don't see the exponent, we do have a variable, and this is kind of like an invisible 1. So the degree would be 1. And if the degree of your function is 1, that means it is a linear function. Think about that this resembles y equals mx plus b. So this is the equation of a line where the y-intercept is 4 and the slope is 1. Hence why it's called a linear function. In this particular example, we have 2 terms. And any function with only 2 terms is called a binomial. Bi meaning 2. For 4x squared, the highest exponent is 2, making this a quadratic function. This particular function has only one term, so this is also a monomial. So basically what we're doing here is we're classifying by the degree, and we're classifying by number of terms. For 2x to the third minus x squared plus x, the highest exponent is 3. And if the highest exponent is 3, that makes this a cubic function. Here we have 3 terms. And if you have 3 terms, that is called a trinomial. Tri meaning 3. For 2x to the fourth plus 5x squared, the degree here would be 4. And this is called a quartic function. Quartic, quart for cuatro, right? So 4. Here we have only 2 terms, making it a binomial. For this last one here, x to the fifth plus 3x to the fourth minus 7x plus 1, the degree is 5. And when you have a polynomial of degree 5, that is called a quintic polynomial. Here we have 4 terms. Anything with more than 3 terms is just considered a polynomial. So even though binomials and trinomials are also considered polynomials, because polynomial is simply when you're adding or subtracting multiple terms, binomial, monomial, and trinomial are just more specific classifications of polynomials. For anything that has a degree of higher than 5, it does not have a specific name. So for example, if the degree was 6, we would just call it a 6th degree polynomial. If the degree was 7, 7th degree polynomial, etc. Now, like I said, at the end of this lesson, we want to be able to graph polynomial functions. So basically what we're going to do here is we're going to get information, as much information as possible from each polynomial, to that way be able to put that information on the graph. The first thing that we're going to look at is the end behavior. As a reminder, end behavior is what your graph is doing at the end. So we have always two end behavior statements for every graph. We have the left side and we have the right side. So we're going to examine how to find the end behavior just based on the equation. What we're going to do is first determine what the leading term is. And the leading term is always the term that has the highest exponent, or rather the degree. If that leading term has an even exponent, that means that the ends will be the same. If it has an odd exponent, that means that the ends will be the opposite. Now if you have a positive coefficient, that means that the right side will go up. If it has a negative coefficient, then the right side goes down. So basically, your coefficient will always tell you the right side. And then the exponent will tell you if the left side will go in the same or in the opposite direction. So here we have the example f of x is equal to negative x squared plus 2x minus 2. The leading term is the one with the highest exponent. So it would be negative x squared. In this case, the degree is an even number, and the coefficient, remember the coefficient is the number attached to the variable, which is -1, is negative. So what does that tell me? Since the coefficient is negative, that means that the right side would go down. And since the exponent is even, that means that the left side will go in the same direction, so also down. And we can see that on the graph, down and down. For this next one, we have x to the fourth minus 3x plus 2. In this case, my leading term is x to the fourth. The degree is an even number. And the coefficient, even though we don't see it, it's an invisible one, and it is positive. So this means that the right side will go up, since the coefficient is positive, and since the exponent is even, the left side goes in the same direction. So you can see on the graph here that it goes up and up. For x to the third minus 2x squared plus 2, the leading term here is x to the third. The degree here is odd, and the coefficient is positive. So since the coefficient is positive, that means that the right side goes up. And since the exponent is an odd number, that means that the left side must go in the opposite direction, so down. So a trick here would be to remembering O for odd, O for opposite. So you can see here on the graph that the left side goes down and the right side goes up. Last one here, we have negative 2x to the third plus 4x minus 2. My leading term here is the negative 2x to the third. The degree is an odd number, and the coefficient is negative. Since the coefficient is negative, that means the right side goes down, and since the exponent is odd, odd for opposite, the left side will have to go in the opposite direction, so up. And again, you can see that on the graph. Left side up, right side down. So to kind of wrap this all up, I have here this chart where if an, which is the leading coefficient, is positive and the exponent is even, it will go up and up. And if the coefficient is positive but the exponent is odd, then it would go down and up. And then vice versa for when your coefficient is negative. This is a reminder of how to write end behavior. It always starts off with as x is approaching negative infinity, which is the left side of the graph. So our left arrow, when we draw it out, And as x is approaching positive infinity, recall that that is the right side. And really the only thing, oh, I wrote it here, but it's here. And really all we're filling out is what the y values are doing here. But the statement, this is basically like a sentence frame. It's always going to be the same. Now here, if I had you in class, we would most likely do this end behavior dance. Now let's practice that leading term test. So I put here to ask yourself those three questions. What is the leading term? In this particular case, my leading term is 4x to the third. My exponent here is an odd number, and the coefficient is positive. Since my coefficient is positive, that means the right side goes up. And since the exponent is odd, that means the left side must go down in the opposite direction. So now we're ready to write out those end behavior statements. As x is approaching negative infinity, f of x is approaching, remember this is the left side, so I look at my left arrow. Since it's going down, we would say f of x is approaching negative infinity. Now for the right side, as x is approaching positive infinity, f of x is approaching, now the right side is going up, so we would write positive infinity. In this example, my leading term here is negative 2x to the fourth. Since my coefficient is negative, that means that the right side will go down. And since the exponent is even, that means that the left side goes in the same direction, so also down. So now let's write those end behavior statements. As x is approaching negative infinity, f of x is approaching negative infinity. And as x is approaching positive infinity, so the right side, my right arrow is also going down, so we would put negative infinity. Now that we have the leading term test, the next thing that we need to look at are the zeros of the polynomial function. The zeros, as a reminder, is just another word for the x-intercepts. And we call it a zero because that, in order to find the x-intercepts, we make y equal to 0, hence the zeros. Now, based on your equation, you can actually figure out how many x-intercepts you're supposed to have. Whatever your highest exponent is, that tells us how many x-intercepts we should have. So since the exponent here is 3, that means that I should have 3 x-intercepts. That degree also tells us how many turning points we should have. A turning point is when your graph changes from increasing to decreasing or from decreasing to increasing. And it basically occurs wherever you have any extrema, which are your minimums and maximums. I put here that in order to figure out how many turning points, it will have at most n minus 1 turning points, meaning the degree minus 1. Since the degree is 3, subtract 1, we would have 2 turning points. And we can see them here, 1 and 2. Now it says at most, we could have 2 turning points or less, but no more than 2. Now we also said we would have 3 x-intercepts. Now how to find those x-intercepts, we would have to factor. So in this equation, we have x to the third plus x squared minus 6x. We're going to make this equal to 0 and factor. Every single term here has an x in common, so we can factor that out. And when you do that, you would have x squared plus x minus 6. What you have inside of the parentheses is another quadratic equation. So with this quadratic, we can factor like we normally do. Open your 2 parentheses and think of the 2 numbers that multiply to give you negative 6, but add to give you a positive 1. Those 2 numbers would be 3 and negative 2, making our factors x plus 3, x minus 2. Now that my polynomial here is completely factored, we take each individual factor and make it equal to 0. Now we take each factor and we solve for x. Here there's nothing to solve, so x is equal to 0 is one of my x-intercepts that we can see right there. Here I would have to subtract the 3. So x is equal to negative 3 is another x-intercept. Again, we see that here. And finally, for the last one, we would have to add the 2. So x would equal to 2 is my final x-intercept. Let's practice that a little bit more. We have here g of x is equal to 3x to the third minus 9x squared plus 6x. Just based on the equation, since the degree is 3, I should have a total of 3 zeros. And because I have 3 zeros, that means I would have one less number of turning points, so 2. Now let's figure out those zeros. We're going to take my equation and make it equal to 0. And now I'm going to factor. Every single term here can be divided by 3. And every single term has at least one x. So I'm going to factor out a 3x. That means that I'm going to divide 3x from every term. 3x to the third divided by 3x is a positive x squared. Negative 9x squared divided by 3x is negative 3x. And 6x divided by 3x is a positive 2. And now we can continue factoring this quadratic. So we have 3x, and the two numbers that multiply to give me 2, but add to give me negative 3, are negative 1 and negative 2. So x minus 1 and x minus 2. And now we set each individual factor equal to 0. Here I would have to divide the 3, and 0 divided by anything is 0. Here we would add the 1, so x is equal to 1, and here I would add the 2, so x would equal to 2. So my three x-intercepts are 0, 1, and 2. So that's a way of checking if you're on the right track. If we said we would have 3 zeros, we should have 3 on our list. Let's try this other one. Here we have the equation h of x is equal to 2x squared minus 12x minus 32. If I look at each individual term, everything can be divided by 2. So I'm going to factor out a 2. And that would give me x squared minus 6x minus 16. I can keep factoring this quadratic that's in here. So I have 2, x minus 8, x plus 2. Since negative 8 times positive 2 is negative 16, and negative 8 plus 2 is that negative 6. Now, based on the equation alone, we see that we're supposed to have 2 zeros with a maximum number of 1 turning point. If you look at your factors, in this one we set each individual factor equal to 0, including this 3x because it had an x. But here this is just 2. 2 will never equal to 0, so we do not set this equal to 0. The only factors that you set equal to 0 are the ones that include x. So x minus 8 would equal to 0, and x plus 2 is equal to 0. These would be my only two x-intercepts. So we would add the 8 over. So x is equal to 8. And here I would subtract the 2. So x would equal to negative 2. So my two x-intercepts, like I stated, were 8 and negative 2. Now that we got how to find the x-intercepts and behavior, let's see how we can put this on the graph. And I have some steps here to help you figure this out, but basically I'm just going to summarize. So first we're going to find those zeros. Notice that in this particular function, it is already in factored form, so we don't have to take that extra step of factoring. We would just set each individual factor equal to 0. So x equals to 0, x plus 2 would equal to 0, and x minus 3 would equal to 0. That would give me our x-intercepts of 0, negative 2, since I would have to subtract the 2 here, and positive 3, since I'd have to add the 3 there. Now to figure out the leading term of a polynomial that is factored, we could certainly do one of two things. We find the leading term when the polynomial is written in standard form, meaning from highest exponent to least. However, this is in factored form. You can either multiply everything out so you can find that leading term, but there's a shortcut. And that shortcut would be to multiply the leading term of each factor together, meaning all of those x's. So I would multiply x times x times x, which is x to the third, and that is my leading term. So that's a little bit easier than having to multiply everything out. Based on this leading term, since the leading coefficient is a positive 1, that means that the right side will go up. Since the exponent is odd, the left side goes in the opposite direction, so down. So now how do we graph this? The first thing we could definitely do is plot these x-intercepts, since those are coordinates that I know. So we have 0, negative 2, and 3. Now I can take my end behavior and attach it to the ends. So the left side is going down. So I'm going to go to my left x-intercept and go down. My right side is going up, so I go to the right x-intercept and go up. Now we need to figure out what's going on in this middle section. Now it's important to note that when we're graphing these polynomials, it doesn't necessarily matter how far and how low we go in between. We're getting more of a general idea of what the polynomial is going to look like. So how we get more or less what this section and this section is doing, we pick x values that are in between the x-intercepts. So for example, between negative 2 and 0 is negative 1. And between 0 and 3, you can choose either 1 or 2, does not matter. Let's say 1. Now what I'm going to do with this chart here is that in this middle column, I have here the factored form of my polynomial. What I'm going to do is I'm going to plug in this x value for every x, but I don't really care about the number. What I care about here is the sign, because if I get the sign, then I know whether I'm going to go above the x-axis or below the x-axis. So let's say if I plug in negative 1. If I plug in negative 1 into x, which is my first factor, that would give me a negative number. If I plug in negative 1 into x plus 2, then that would give me negative 1 plus 2, so a positive number. And if I plug in negative 1 into x minus 3, negative 1 minus 3 is negative. Then what I do, since all of this is multiplied, I get the sign that I would receive if I were to multiply these three signs together. A negative times a positive times a negative is a positive number, meaning that my graph here between negative 2 and 0 is positive. So that means I go above the x-axis and I connect to the next x-intercept. Now I do the same thing, but for 1. So if I plug in 1 into x, that's positive. 1 plus 2 is also positive. And 1 minus 3 is negative. A positive times a negative is a negative number. So I would go here below the x-axis because I end up with negative. And that is how I would get my polynomial graph. Let's try this again with another function. Here we have negative x minus 4 times x minus 1 times x plus 1 times x plus 2. In order to determine that leading term, you're going to take everything together and multiply it out, or rather the x's. But if you ever have a sign here in the front, you have to take into account that that leading term is going to be negative. So we have a negative times x times x times x times x. So my leading term here is negative x to the fourth. Since my coefficient here is negative, that means that the right side would go down. And since the exponent is even, that means that the left side goes in the same direction, so down as well. So for my end behavior, as x is approaching negative infinity, my left side, f of x, is approaching negative infinity. And as x is approaching positive infinity, my right side is also going down, so I would write positive infinity. Now my zeros are when each individual factor is equal to 0. So x would equal to 4, 1, negative 1, and negative 2. And I got that by setting each individual factor here equal to 0 and solving for x. So for example, for this first one, I would have to add the 4, which is why it's a positive 4. Add the 1, positive 1, etc. So once you have your zeros and your end behavior, you're good to start graphing. So I'm going to go ahead and plot these x-intercepts. We have 4, 1, negative 1, and negative 2. My end behavior is down and down. And now I'm going to pick values in between each x-intercept. So between negative 2 and negative 1, I'm going to say negative 1.5. Between negative 1 and 1, 0. And between 1 and 4, you can pick 2 or 3 or anything else, and I'm just going to pick 2. So now we're going to get the sign, keeping in mind that because of this negative, you're going to have a negative for every single one. Now when I plug in negative 1.5 into every x, negative 1.5 minus 4 is a negative number. Negative 1.5 minus 1, also negative. Negative 1.5 plus 1, negative. And negative 1.5 plus 2 is positive. If you multiply these 4 negatives together with a positive, you get a positive number. So my graph here is going to go up. Now remember, I don't care how high or how low you go when you're doing these dips and hills. Okay, it's basically you're just getting a general idea of what the curves of your graph are doing. Next, when I plug in 0, 0 minus 4, negative. 0 minus 1, negative. 0 plus 1, positive. And 0 plus 2 is positive. And if you multiply 3 negatives with 2 positives, you get a negative. So here it's going to go below the x-axis and connect. Moving on to 2. 2 minus 4, negative. 2 minus 1, positive. 2 plus 1 and 2 plus 2 is all positive. 2 negatives times 3 positives gives you a positive number. So we go above the x-axis and connect to the next x-intercept. So this is my graph. And you can see here that based on my leading term, I had 4 x-intercepts with 3 turning points. Now we're going to look at one other property of these zeros. When you look at this equation, if you were to write out the zeros based on the factors here, you would have that x is equal to 0, 1, negative 2, and negative 2 if you set each individual factor here equal to 0. What's different about this example is that x is equal to negative 2 repeats. And it repeats exactly 2 times, so twice. Now, this is called multiplicity of zeros, when an x-intercept repeats multiple number of times. If the multiplicity of a 0 is odd, that means it will cross the x-axis. So if you see that an x-intercept when you solve occurs 3 times, 5 times, 7 times, 1 time. Those are all odd numbers, so it would cross the x-axis. See here at x is equal to 0 and 1, it crossed the x-axis. It started positive and then it went to negative, and then it started negative and it went to positive. So it went across that x-axis. However, if the multiplicity of a 0 is even, such as at x is equal to -2, it repeated 2 times, which is an even number, that means it will only touch the x-axis. So we see here at x is equal to -2, it touched it, but it didn't go across it. It went back in the same direction. So it started positive and it stayed positive. Now, I put here that determining the multiplicity of a 0 can also be based on the exponent of each factor of the polynomial. So for example, this polynomial up here is actually more precisely written as x times x minus 1 times x plus 2 squared, since there is 2 of them. If it was 3 of them, then the exponent was 3. If there was 4 of them, the exponent would be 4, etc. So how does this help me graph? If you understand multiplicity, you actually don't need to do the chart, but I'm going to show you both ways anyway. So we have here x to the 4th minus 2x to the 3rd minus 8x squared. In this example, my leading term is x to the 4th, and I need that in order to determine the end behavior. Since the coefficient is positive, that means that the right side goes up. And since the exponent is even, that means that the left side also goes in the same direction, so up. So for both of these limit statements, since both ends go in the same direction and it's up, both of these limits would go to infinity. Because of the exponent, since it is to the 4th, that means that we're going to have 3 turning points, and we're going to have exactly 4 x-intercepts. Now let's actually find those x-intercepts. We're going to need to factor. So when you look at every individual term, they all have an x squared in common. So if I factor out an x squared, I would get x squared minus 2x minus 8. And what's inside parentheses here, we can actually factor even more. So we have x squared, and then this could be factored to be x minus 4, x plus 2. Let's make this equal to 0 so we can solve. X squared is equal to 0, x minus 4 is equal to 0, and x plus 2 is equal to 0. For this first factor, I'd have to square root, but the square root of 0 is 0. So that is my first x-intercept. For x minus 4, we would have to add the 4. So x would equal to 4. That would be my second x-intercept. And for this last one, we would subtract the 2. So x would equal to -2. Now we said we would have 4 zeros, but we only really have 3. And that's because at x is equal to 0, look at the exponent. Remember, the exponent tells us the multiplicity. That means that x is equal to 0 occurs twice. So technically, we do have 4. We have 2 zeros, 1 4, and 1 -2. If the multiplicity is 2, that means that my graph will touch the x-axis because of that even multiplicity. At x is equal to 4, this only occurs 1 time, and 1 is an odd number, so it will cross. And the same thing for x is equal to -2. This only occurs 1 time, so it will cross. So I'm going to show you how to use your multiplicity to graph if you don't like using the chart. So I'm going to put my x-intercepts on the graph here, 0, 4, and -2. My graph goes up and up, so I go up on the left side and up on the right side. At x is equal to -2, we said that because of the multiplicity that it would cross. So that means that here, instead of going back up, I would go down. because it has to go across the x-axis. At x is equal to 0, we said the multiplicity is 2, meaning it only touches the x-axis. So it's not going to go above because then it would have crossed it. We're going to go back down and then connect to the next x-intercept. And then here at x is equal to 4, we said the multiplicity was 1, so it would cross. And because we already attached that end behavior, we do see that it crossed the x-axis there. So I'm basically done. This is the graph of my polynomial function. However, if you want to double check your work and you want to do your chart, here in this empty space, you would put the factored form of the polynomial. It's a lot easier to figure out the sign if you use the factored form, which we had gotten x squared times x minus 4 times x plus 2. Now we would choose x values in between the intercepts. So between -2 and 0, we'll use -1. And between 0 and 4, we'll just use 1. And now we plug it in. -1 squared would end up being positive. -1 minus 4 is negative. And -1 plus 2 is positive. A positive times a negative times a positive is a negative. And you can see how it goes below the x-axis at that section. If I plug in a positive 1, 1 squared is positive, 1 minus 4 is negative, and 1 plus 2 is positive. And again, giving us a negative number. And you can see how the graph is below the x-axis there as well. Let's try one more. Here we have x to the third minus 4x squared plus x. My leading term here is x to the third. Because of this positive coefficient, that means that the right side will go up. And since the exponent is odd, that means the left side would go down. Meaning that for my end behavior statements here, as x is approaching negative infinity, that is my left arrow, it's going down, so negative infinity. And as x is approaching positive infinity, that's the right arrow, I see that f of x would also go up. Based on my degree, since this is a cubic function, that means I'm going to have exactly 3 x-intercepts and only 2 turning points. Now the turning points doesn't necessarily help us in the graphing process, but it does help us to make sure that we're doing this correctly. So for example, here, we said that we would have at most 3 turning points, which I have one here, here, and here as well. So only 3. If you had more than what you were supposed to, then you know something went wrong and to try again. Now let's figure out those x-intercepts. From every single term here, I can factor out an x, which would leave me with x squared minus 4x plus 4. If I continue factoring, the two numbers that multiply to give me positive 4 but add to give me negative 4 would be -2 and -2. So x minus 2 times x minus 2. Now since this factor repeats 2 times, I would rewrite this as x times x minus 2 squared. We make this equal to 0 and solve for each factor. So x is equal to 0 and x minus 2 is equal to 0. Notice that I didn't use the exponent here. The exponent just tells us the multiplicity. But to figure out the 0, you can just take the factor that's in the parentheses and solve for x. So here, this is one of my x-intercepts, which is at 0. And over here, I'd have to add the 2. So x would equal to 2 is my other x-intercept. And I actually don't have a third one here. So x is equal to 0, no exponent. Multiplicity is 1. So that means it's going to cross the x-axis at that point. At x is equal to 2, the multiplicity here is that exponent, which is 2. So that means it will touch the x-axis. So now let's do this without the chart, and then I'll verify our answer using the chart. We have those two x-intercepts at 0 and 2. We're going to attach the end behavior now. So the left side goes down and the right side goes up. At x is equal to 0, we said that the graph will cross. So that means that here I'm going to go above the x-axis and connect to the next. Now I'm basically done here since I only had these two x-intercepts. But we can verify, right? At x is equal to 2, we said that it would touch. Now because I had already attached my end behavior here, we do see that it touched the x-axis and then it went back up. So everything looks good. Now let me show you using the chart in case you prefer using it this way. We have x minus 2 squared. Remember to use the factored form here. We only have one space in between, so we're going to use x is equal to 1, and we don't need this extra column or row. If I plug in 1, this would be positive. And if I plug in 1 here, 1 minus 2 is negative, but it's being squared. And anything squared is positive. Positive times a positive is positive. So we can see in between those x-intercepts that it is above the x-axis. And that's how you graph polynomial functions.